Okay, so a quick look through the code here just to refresh your memory. There's the tree class. The tree class is going to have tree nodes that are used to hook things together. If you go and look at what a tree node is just like we had for, it's a node just like we had for linked lists. It's got the thing that we're trying to store, but instead of one link to go just in one direction, it's got two links, either left or right, going downwards. So it's left going down, right going down, the way we're drawing our tree. And the constructor just stores things away. The compare to for tree node is sort of sneaky. The compare to for tree node just passes the buck. It says if somebody says, hey, you tree node, compare yourself to another, the tree node just says, oh, you weren't really interested in me, you were interested in the thing that I was holding and the thing that he was holding, so we'll just call them to do the compare to and give back the result. So it's like ducking your head and going, I'm really not the interesting person here, those guys are. Let them do the work. In order for us to be able to call e's compare to, we have to guarantee that the compare to actually exists. So the e things that are put into the tree, whether they be students or drinks or VIPs that want to get into a lineup or whatever it happens to be, anything that's going to be ordered, we have to have a compare to available. And so at the top of the class, that's why you've got that little gobbledygook there that says, the e things that we're putting in the tree had better say implements comparable to advertise that they have a compare to, because the only way that we can allow things to go into the tree is if we can somehow organize them as less or greater than. So they got to have a compare to for that to work. So that's these, we'll put e things into the tree, but they better have a compare to. And so if you try to put something into this tree that doesn't have a compare to, the compiler will give you a warning and saying, no, this isn't going to work. Okay. And then we started writing the add method. And we wrote the add method by basically doing silly things first, trying to do the simplest thing we can do, which is just add one element, going, oh, look, we put it into the top, it must work. And then we keep discovering problems with it. So if you put one node in when there's nothing in the tree, that's fine. That's the special case. Now we've got one node in. So again, that's typical of that linked list code. There's always an if statement that says the first one is always a special case. Once you've got one in, then the next time around when you're trying to hook up another one, the question becomes, gee, if I'm trying to hook up another one to already there, do I put it on the left side or the right side of what's already there? Which means you have to call compare to in order to decide left or right. So things that are negative are going to go on the left-hand side, negative meaning smaller than, and things that are greater than are going to go on the right-hand side. Okay? And so this is the simple code, but it will only work for putting just one or a maximum of two things below if they happen to fill out the tree. But we've still got a problem that we don't advance anything lower than just the one level that we've got on the diagram. So a root node plus maybe one on the left and maybe one on the right, and then we're done. And in the tree driver, that was as far as we got, because basically we put Fred at the root of the tree, and then we put one person, Albert, to the left of the thing. So we've just got Fred and Albert hooked up at the moment. And now we have to worry about advancing to a level below. Okay, so just to make this thing a little bit consistent with my diagram here, I'll do another myTree.add to just fill out this other level of the tree and get Steve into the tree. Okay. So that should correspond to the diagram. Fred at the top of the tree, Albert to the left, and Steve to the right. Okay. So now the problem comes along is that somebody says, let's add another one in here. Let's turn around and add somebody who fits on the less than side, which would be maybe Carly. There we go. So the C's need to fall to the left of Fred, but unfortunately our code right now, if you look at it and we try to put something to the left of Fred, it wipes out the Albert that's already there, oops, and replaces it with Carly. Okay? So this code is just going to do a replacement here, which is not what we want. So we've got an issue here that says if that space is already used, that spot is already taken, then we need to recognize that, and what should we do?
Create a new tree node.
What's the smaller problem? If you try to put them in this tree, and there's no room for them there. Go down a level and say, oh, that's like a tree where there's the root of the tree. Go stick somebody in there. Okay, so there's that idea. I removed some information, so it's a smaller problem by dropping down a level, but the problem here is the same one that we already had before. It still doesn't need to be smaller, left or right, etc. So there's some idea that, oh, we could just use recursion to solve this problem. Okay. So let's look at the code that we've got. What was one of the first things that I said that made recursion work? What's the first thing that you typically have to do to get it to work? Go back and look at that sample piece of code when I started talking about it. The issue with the sample piece of code is that there's always something that gets the ball rolling. Okay? So that's the thing that starts the recursion. Here I'll give you the base case yourself, and then the recursive thing takes over from there. So what we've got is the same situation here, is that we've taken care of sticking something at the root node, but if it's not at the root node, maybe then we should start doing recursion. And so what I'm going to do is I'm going to take the code that we have and I'm going to turn this code into a subroutine or a method so that that becomes the thing that we do over and over again for each level. And so what I'm going to do is I'm just going to write, we're going to call this one private void add internal because it's one that nobody gets to see. And what it's going to take is a tree node. We could call it root, but it's just start node or upper node or whatever you want to call it. And I'm going to add the add internal in here to say this is add internal. And I'm going to say the place I want you to start is the root node. And here's the thing I want you to add. Find a place to put that thing into the tree. So add internal actually takes the start node and a tree node, the add node. Or we'll call this one my node again, just to be consistent. Okay, so it's still the same code. All that I did was I just plopped the code that I had into a method, just so that now I have a method to help get the recursion started. Okay? It's exactly the same piece of code. So now the logic is, oh, if we've got an empty tree, we'll stuff something in at the root node. We've got a node in there. If it's not an empty tree, then, oh my God, let's hook this other one into the tree somewhere. Okay? So now you come down and you say, okay, let's try to hook this thing into the tree. And I'm just going to change this word from root to start node. Because it's not necessarily the root of the tree anymore, but it's some node in the tree. Or maybe we'll call it, even better yet, how about if we call it in-tree node? Trying to think of the best name that I can do for this thing to make it completely obvious. Let's try that. Okay, so it looks like that. So for if we've already got one in the tree, like Fred, when we go to hook in the next one, like Albert, we come along and we say, oh, start at the root node that's already there and see whether or not you can plug Albert's node into the tree someplace. And so we compare Albert to the root node, and if it's less, then we hook it on the left of what's the root node. But could be any old node, it just happens to be the root node the first time. Okay, so believe me, code still works. Got our little subroutine in there. Now the fun begins. The problem we said was if we go to hook something to the left, so we've got the situation where Fred is in the tree, Albert is in the tree. When we go to add the next person, Carly, it's like, oops, don't want to disturb that thing. Okay? So the situation we've got is if the left side isn't empty, or sorry, put it this way, if the left side is empty, we can hook it in directly. Okay? So let's change this code to say that, because that's a special case. If the left side happens to be specifically empty, then it's okay to do that stuff. Oops. Let's turn on source format to make it a little pretty here for a second. And once we'd hooked them in, we'll use our rejection. We're done at that point. We'll just get out. What do we do if they're not in the tree? Or sorry, if there's no room? Go down a level. So what we'd try to do is we'd try to add them into the tree using add internal. And the thing that we'd specify is in tree node, which in this case is the root node, but we want the root node's left side. So that's the idea of take the root node, drop down a level to the left side, and give that to somebody else as the work, and say, oh, go see if you can put that thing one level down below to the left, and oh, by the way, the thing that you want to insert is my node. And then I'll put in the return here just so it's, again, obvious. Okay, so now the code reads, here's the person that I want to insert, Carly. Go to insert Carly and say, well, okay, we'll compare Carly to Fred. Oh, Carly needs to be to the left side of Fred. Is this thing empty? No, it's not. So what we'll do instead is we'll give the work to Albert and say, hey, here, Albert, you go see where Carly fits below you. Okay? So I passed on the work with add internal to one level below. Just go take care of it. No value coming back in this case because it's going to get added someplace eventually. Don't really care. And that same code also applies exactly for the other side of the tree. So I'm just going to take exactly this same portion of code and I'm going to morph it into the right-hand side in place of this stuff that we had that only worked for one case. So all of these, instead of left, should say right. So I want to, there's other ways of writing this, but in this case, I want the else's in there because I want to show you that it's either specifically either or, right? And I want to keep the code formatting almost exactly the same, right? So it all looks pretty much identical. So if the comparison is less than 0, it's going to go on the left hand. If it's greater than 0, it's going to go on the right side. Now you can talk about a specific case. Well, let's see if we were trying to put it on the right side. If it's empty already, we'll just hook the node in because there's room for it. If it's not empty already, then I guess what we have to do is drop down one level to the right, give somebody else the problem at one level deeper, and say, here, you try to put that thing in the tree wherever it goes. And that's all there is to it to make it work. And it's recursive. What's the stopping condition? What makes this thing actually ever stop? When you find an empty node. So either you find an empty node to the left or you find an empty node to the right, but sooner or later, if you keep dropping down a level, you're gonna find one of those. So there's this, either it's that or that is the thing that eventually stops it. Buried a little bit in the code, so not as obvious as putting it right at the top. Okay. Gotta hopefully insert it into the tree. Suppose that I now want to do something like ask a question, gee, I wonder if somebody's actually here. I want to look them up and see whether or not they're there. We said the whole reason for having these trees was so that you could go and search for somebody afterwards. So think of this portion of the code as of being, let's go read some file of 1 million people who are all in arbitrary order and let's stuff them into the tree. Okay? Sooner or later, you want to start searching your tree for things. So when we're searching, what are we going to have to do? If we go my tree dot search, give the person to search for. What's the trick to the game here? Special trick. Make a fake person. So you don't want to say Fred there because you wouldn't at some point have Fred anymore. And notice that these guys, I specifically didn't give them a variable name to remind you that you couldn't get at them. So the only way that you can search for somebody is to actually make a fake one. So we'll do that here just to make it obvious. We'll do worker fake Carly is new worker, somebody who looks like Carly, but obviously not the real Carly because some of the information is missing. And then we'll call search on the fake one. What is search going to give back? True or false, we can do better. And second answer was position, but there's no position and there's no numerical position in this tree that's going to help you. What would you expect to get back?
Original object.
The original Carly, right? So the thing that's going to come back here is the original one, which you would then print out or extract some information from. Okay, so let's go write the search function. So the search function is going to look like this. It's going to be public e-search e-fake. So I'll give you a fake one, and you give me back the real one. What's the simple Pfeiffer trick when somebody says return something?
Return no.
Make a variable and then send it back. So let's make an e found item is empty, and then we'll return the found item, whatever it happens to be, and then worry about how to actually make it work. I got that in the wrong place, I think. Yeah, it needs to be where? Okay. Want to do this recursively. What's the trick to the recursion? Follow the same pattern as what we did for add. Create a starting thing. So we used add internal here, starting at the root to get the process going. So the same trick we'll pull down here with search. We'll call search internal. Write it this way. Found item is talk to search internal, and we're going to give them the place to start, which is start hunting at the root of the tree. And what's the thing that you're going to ask them to find? You could try doing fake in there, but fake is a worker, and what's root? Root is a tree node. So two ways to go about this. You can either deal with actual e things, so do root.thing to store against the fake, which would make e versus e thing, or you can compare node versus node. So the trick to the game here is just to be consistent. Since the tree's got nodes internally for everything, I'm going to take the fake and I'm going to say and make a new node and drop the fake in it. So I'm actually going to pass in a fake node with the fake thing inside it. And now I've got comparing node to node all the way through the tree. And that's a tree node. And we have to write search internal, which is now private. And search internal is going to take a tree node that's, what did we call the last one? In tree node, someplace in the tree, along with a tree node that's find me, or match me, I guess. Yeah, we'll call it find me. So now let's think recursion here. What would be the lucky case? You found them because what would say that you'd found them? How would you know that they were a match? Equals would be a match. Now, here's an interesting thing about trees. Trees never use equals. They use compare to, because if you're neither smaller than or larger than, you must be equal. Okay, so what we'll do is we'll still use compare to, so we'll do comparison is in tree node, or actually we'll do it this way, find me compared to in tree node. So we'll compare them, and if they match, neither greater nor larger means exactly the same, then we'll send back what? The in tree node. The find me is the fake one, right? Maybe this one would have been better written as the word fake, just so that we don't ever use it for something real. So in tree node dot, and it's got to be not the node itself, but thing to store, which is what the node was actually holding on to. Okay, so there's that idea with recursion. The best thing you can do for yourself is think of the simple cases. So there's found. How would you know if you hadn't found it?
Anything else? Anything but that?
Well, what would be the absolute simplest case when somebody says, here, I want you to go find something that looks like this in here? What would be the good thing about the here that would limit the amount of work that you had to do? There's nothing there. So the simplest case that you can ever have is, oh, go search for this thing, empty pile. Oh, well, that's easy. Okay, so recursion, always think of the ultimate in easy cases. So how would you know if the pile was empty? If tree node is empty, they said, here, go search through this empty stuff, and then you know that it can't possibly be there. So in that case, we'll send back a null to say we couldn't find it. Okay, so I've taken care of the two easy things. Somebody sends me empty, done. And as a matter of fact, just to be careful, because that is a null thing, I'm going to cut it out of there, and even before I do the comparison, I'm going to stuff it in there. Because that's the worst case. If it's null, I don't want to ever use it, so we'll reject it right away. So there's not found. Can't possibly be found if you didn't give me anything to look in, and otherwise I'll go and I'll see whether or not I can find it for just this node. Now what? We did the easy cases. Now it's phone a friend time. If it's the comparison is less than 0, so not just -1, it could be quite a bit bigger or smaller. Phone a friend, which is called search internal again, and this time say, oh, you need to search, somebody else needs to search on the left side of the tree for the same thing that I was looking for. And if you find, it's either there or not there, whatever it says, whatever the person below me says, found or not found, that's the thing I punt back upwards. And there's an else there, and even though I don't have to code the else, I'm going to do it just to make it obviously symmetrical. If it's not on the left side, then I guess we should be searching the right side instead. And so we'll call somebody else to say, hey, go look on the level below on the right-hand side, see if you can find this thing. Drop down a level, go. Whatever you say is fine with me. If you don't find it, I'll pass the word along. If you find it, I'll take the thing you gave me and I'll pass it along. happy with that. I haven't had to do any work, just sitting here waiting. Think it'll work? Notice that when we did this, at no time have I worried about what happens below any level other than just this one for me. If I can get the instructions right to work just for me, trust me, it will work for the thing however large it happens to be. Well, let's just try it. And we'll print out and let's just double check and see whether or not worker actually has a 2-string. Would we be so lucky? Yep. So let's just run this thing and see what happens. Found Carly. Somehow magically. With all, notice that's all of the information, and you know that that's the right one because the fake one didn't have anything in it. Now this obviously is an exhaustive test, but hey, it looks like we can add things into the tree and we can turn around and search for them again. Anything else we should do with this tree? Any other method we might want to write? Remove is tough. We'll get to that. Something simpler. Suppose that I wanted to see all of the items that were in the tree. That would be a reasonable thing to want to do. Print out all of the items, because it doesn't really change the tree, which remove does. It just says, let's just go look and see what's there. Well, let's talk about a recursive solution. The way that the for loop or whatever that we want to write from the driver program is going to work is, let's just assume it was a counted loop or whatever. It's going to say for everything in the tree, go get me, hey tree, go get me the first one. Hey tree, come after you've gotten that one, come back and get me the second one. The question is can the tree do that? Is there any numbering to those things? Even if there was a numbering and you went 0, 1, 2, 3 and just did them in order, level by level by level, every time that you went and got one and said go get another, it would either have to restart from the beginning of the tree to do the numbering, or it would have to somehow magically remember where it had left off. Okay? Now, we did that for iterators for a linked list. We said, oh, iterator is easy for a linked list. It can remember where it left off really easily. We're just standing over the next thing on the chain. How do you remember if we had a node pointer here? Do you think the node pointer could remember where it had left off? What information would it need to remember where it had left off? Think back to our example of the forest when we were using a to-do list. Yeah, the to-do list had the places you haven't searched yet. So if I wanted to go through and somehow print out all of the stuff, I would have to remember all of the places I hadn't been to yet every time I went back and returned one thing to somebody, so that then I could go back when they said get me another one, I could go, well, here's the ones I haven't been to yet. Here's basically my current state. So you'd have to remember the entire stack in order to be able to keep track of all of the stuff that you hadn't done yet. That would work if you actually had the stack in your hands, but in this case we're using the Java stack, So there's no way that you can remember from one time of going through hunting for things to calling the next time where you were partway through the process in order to get back to there. All of that state is completely hidden from you. So basically what I'm saying is that it's not possible to keep a single tree node reference to this stuff or keep enough information to be able to exit from this thing and then come back and continue in this printing process one at a time. What we're going to have to do is somehow assemble the entire completed thing into one thing that we give back to them and run the recursion all the way through to produce a result and send back the entire result at once. You can't escape the recursion halfway through.
Couldn't you push the tree nodes on the stack?
You could push tree nodes on the stack, but then you have to have the stack, you have to remember the stack. It has to, the next time you come through, you have to go, oh, okay, I gave them this one off the stack, but now I have to go and either make the stack bigger or smaller, or add or subtract. And so it becomes a big issue in where do I keep the stack and how do I manage it? Okay? Because I mean, you know, the equivalent is in the phone a friend thing, right? You know, I'll phone two people and you phone two people. You're saying, oh, okay, if we want to find out who everybody who's on this list, the way we've done things that way, we're going to have to somehow stop the thing halfway through. All right, everybody stop right there. We need to know exactly how far we've gotten in the fan out so that I can remember to just print out just this one that's the farthest we've gotten. So that come back, oh, okay, you people can continue on fanning out. Right? It's difficult to do. It's easier to say, let's just produce the entire list, zing, have everybody dump stuff onto one list, and then we'll go get the list back. Okay? So the trick here is if we're printing things out, what the driver is probably going to do in order to print them out is we're going to have something that looks like this. A list of worker all workers is talk to my tree and say give me a my tree dot get all workers. Something like that. Okay, produce a list. Let's start it a little easier though. Let's do something that I've always wanted to avoid. Instead of calling it get all workers, oh, I'm going to hate myself, but I'm going to do it anyway. Let's call it print all workers. And let's go into the tree class and quickly write print all workers in almost no time. Here's print all workers. What should print all workers do? Think recursively. What's the first thing you do with a recursive routine? Prime the pump, so print internal again, and we'll pass it the root of the tree. Start there. Start printing from there. Well, print internal is private, and print internal is going to take tree node, whatever the node happens to be. Tom Sawyer thing. For just this node, what's the work I have to do? Well, there's no list yet. I'm just, forget the list. Let's just print it. This is where I'm going to print directly from the tree class, even though that's a no-no. We'll fix it in a bit. Let's do the simplest thing. There's my work. What's the simplest amount of work I can do? Not the left or the right. Just the current one, right? Just the single one. So we'll do it as a node dot thing to store. Okay. Now let's get some other people to do the work. if I printed out my node, what's the work that's left? I said do this one.
Print left to right.
Somebody has to print the left. Hey, you do the left. Somebody has to do the right. So it's print internal somebody to do the left and print internal somebody to do the right.
Keep up order though, we want the,
Well, we'll get back to order in a second, okay? So this is, I'm gonna do the work that has to be done for my node, and then I've got a friend that's gonna take care of everything that's underneath me on the left, and another friend that's gonna take care of everything underneath me to the right. When would we ever stop? What's the degenerate case? When A node's null. Somebody says, here, print this, they drop down a level, and there's nothing in the tree at that level. I got an empty tree. Oh, well, that's really easy. So we'll just change this thing to say, if for some reason a node is empty, then nothing to do here. So there's that rejection case that's really typical also of recursive code. Okay? So there's the entire print routine. Now, if you want to make them come out in order, we said the other day that now this thing really belongs on that side, because that's go do anything that's smaller than me and get it said first, then I'll say my stuff, then go do anything that's larger than me and get them to say their stuff. Well, let's just give this a try, shall we? Let's go back into tree driver. I'm just going to comment out this one that was just the finding, and we'll just run this thing with the print statement. Look, not only do they all get printed out, but what order did they come out in? Sorted order, smallest to largest, because the tree is maintaining the order, and we're always going through it when we process it, smallest to largest, left side, middle, right, and so when they get printed out, they come out in sorted order. That is what's known as a tree sort. Stuff things into a tree, pull them back out. When you call them back out of the tree, they're all in sorted order. Very, very efficient way of sorting things. Okay, so there's the print, and if you go and look at the code for it, code's pretty trivial. There's the joy of recursive code again. There's not a lot of humming and hawing about it. You just put the blinders on and go, what do I have to do for me? Where can I find somebody else to do some work for me? What's the reason why I would have nothing to do? And something to start the ball rolling. And there's just the simplest case of recursion that you can do to get it. Okay? Now, for tomorrow, or sorry, for Tuesday, I guess, we've got this nasty little print line in there, and you know that I don't like print lines in anything but the main program, so that's a problem. So what should I do there? Put them in a list. And so what we can do is we can change this code to have print all workers make an empty list to start with, and then pass that list through to the recursion, and anytime somebody says, instead of printing something out, they just dump their thing onto the list. And then we'll send back the list, so we'll change this from print all to, you know, give me a list of all or whatever. So we'll make that change so that the print statement gets up to the level that it's supposed to be. So we'll just form the list. And we're done for the day.